Okay, so good morning, and so today will be the last lecture on, what I consider the formal aspects of classical mechanics. There's a lot more to do, but I think we need to do more mundane things in this course. So, okay, so today is so 2 lectures ago, because the last lecture was given by Dr. Arun, we studied the Hamilton-Jacobi equations. Okay, so the idea was we have some variables Q and P and a Hamiltonian of Q and P, and we try to make a canonical transformation to some new variables where the idea was that of type F2, and where H prime was 0 in the new variables. Q and P. And few features where P came out as integration constant. Okay, so when H prime is 0, both Q dot is 0 and P dot is 0, and this just implies that Q and P are constants. Slightly boring, but okay. This is what it implies. But today we will do something slightly more interesting, different, which is closely related to this. We will try to go from Q, P, and remember I said even though I read Q and P, it could be any number of degrees of freedom, not just one. With Hamiltonian HQP, we try to get new variables, which we will write as theta and I. Okay, these will be angle variables, and these we will call action variables. Sorry, I mean the word action is misused, is overused, and the Hamiltonian will be a function of all these. Okay, so we already saw this. So then theta dot will be dh by di, and we'll just call this some omega. And in general, this will be a function of I. So then theta will be omega I is t plus some initial value. And of course, I, so we can put variables here, a, okay. So we will see how to do this, and we'll start with we'll start from the simplest case. One degree of freedom, and we'll assume that the Hamiltonian is time independent. Okay, and so that implies the energy or the value of the Hamiltonian is a constant of motion. And that came out as an integration constant while we did the Hamilton-Jacobi theory. But here we don't want, so what we will do, I will now construct something. Okay, so let's also further assume that h of qp is p squared upon 2m plus some v of q, some arbitrary potential, and E is a constant of motion. What we will do is we'll construct a new function. So E is not the suitable variable which we should use. Consider a new function defined as follows. Okay, so I need to explain things a little bit. So let us just do the following thing. So let's say we have some potential like this. This is V of Q versus Q, and let's take some energy. Okay, very good. Okay, so these are two turning points. So let's call this Q1. Let's call this Q2. That's for the same energy E. What did I know? And this is the value of energy. So what we have is we see two kinds of orbits, one which is bounded between Q1 and Q2, and second set of orbits which are bounded between Q3 and Q4. So we'll focus, let us focus on the periodic orbit. Sorry, I forgot to mention, here we want to think of theta as angle variables, okay? So we'll write that theta A belongs to circles, okay? And with period which we write as 0 to 2 pi, okay? So for instance, a classic example which will not fit into this framework is a free particle, because for the free particle, there's no angle, it's unbounded, and so it can go from plus infinity to minus infinity. So what we will do is we want to restrict ourselves to situations where the orbits are bounded, they lie within a box, large enough box. Okay, so we'll focus on the periodic orbit where Q belongs to Q1 and Q2, the two turning points. Okay, so that's what.
So,
Yeah, go ahead.
theta is the same generalized coordinates as the theta we use in the plane polar coordinates.
No, nothing.
Okay.
No such thing.
Okay.
It's just some circle.
Okay.
Okay. So I mean, so for every A, so you would write that S1 cross S1 times Cartesian product of S1. Okay. This is called, if there are n degrees of freedom, this is called the n torus. Okay. So so a point on this is for Cartesian product is theta 1, theta 2, theta n. Okay. So for two dimensions, I mean, I will point it out that it means it's moving on the surface of a vada, okay, or a bagel, or a donut, whatever you fancy. Okay. So we'll focus on this periodic orbit. So this variable I of E, so this closed circle here indicates that we do it over one cycle. Okay. So we can do this computation, and we have fixed the energy. So we want to do this computation 1 over 2 pi. Okay, closed orbit. What is a closed orbit? Go from, let's say you start from Q1, go to Q2, and come back to Q1, right? But from symmetry or time reversal, you can show that this is equal to 2 times integral from Q1 to Q2 P of, this is what we have, right? I just so this circle in this integral says we do it over one cycle. Okay, so this periodicity is there implicit in this whole story, and so that's what we get, and we have to do this integration. And what is what is P? So P will be plus square root of 2m, because H equal to E, right, from that, and we are choosing from Q1 to Q2, so we choose the positive sign. Okay, 2me minus 2m V of x, V of 2. Okay, so this is what we need to do. Okay, so we and of course these also depend on E. Okay, so this is just after you do this integration, this will be. Okay, so is this clear? So what we will see is that this will be what we will call the action variable. So I is a complete. I mean, it's a function of E. So this we will call the action variable. There will be an angle corresponding to that, but let's hold it and let's do a further now. So what happens? We'll take V of Q. Let's do the case where we can do the integrations easily. Half m omega square harmonic oscillator. Okay. So there, if you give me E, so it's not like this kind, it's just a single well, and of course E should be greater than 0, we know that. Okay, so once we do that thing, we can write this integration. Okay, so let me do it. So Q1 is equal to minus square root of, so it should be, and the integrand becomes 0. So when V of Q equal to E, so that will be so it will be 2E upon this is one turning point, other side turning point is just minus plus okay, so we can write the integral. Okay, so this is an integral you can do exercise. Show that. Okay. So in this case, you can argue with me saying, but I mean, it's just some constant factor omega, which to which it so I and E are more or less the same. I would say yes, but in more general cases, that need not be true. Okay. So for the by carrying out the integration, this you can do easily. Okay, so this is not very hard. So what this says is that E can be written as a function of I now as I times omega, and more so. But E is the value of so I is a constant, so we can write more than so instead of writing it this way, I won't call it E now, but now this I will write it as H prime of I is I times omega. So this is the new Hamiltonian where I, theta and I are coordinates. Okay, and you can see very easily that theta dot is dH prime by di. Okay, so we haven't said what theta is, we'll tell you in a moment, but let's just do this, and that will just tell you that's equal to omega, or theta equal to omega E plus some initial value, theta 1. And I is just a constant, but we also know what I is. I is omega. Okay, yeah, so leave it as that. I is a constant. Okay, so what is the picture that we have? I can take any value. Okay, and so I can be from 0 to infinity because energy is bounded. So this is 0. and this is I. So what this says is that, sorry, not E, I. Okay, so what it says that if you pick a value of I, on this point, there is actually a circle. Okay, so what is happening is that if you give me initial value, the orbit will be a circle. Okay, so if you think about this a little bit more, you can think of it like this. You can think of it as a cylinder. Okay, with angles. So this angle is theta, and this length, that thing is I. And so if you pick a value here, the motion is restricted to be on a circle or a one torus. Okay, so that's what is happening. Okay, but the upper picture is is simpler in the sense that for higher dimensions I can draw some. I can draw pictures which will at least make sense. But this kind of picture, I can only do it for 2D. Okay. So now, but still we haven't answered what is the variable theta. Okay, but we can guess, right? I mean, we can quickly guess this because theta goes like omega t. Okay, so if you remember, the most general q of t would be some amplitude. Okay, so let's write that a sine omega t plus some constant. I mean, at 0, this is kind of thing you would do. And you can see here that that omega t is, so this guy can be identified with theta, but what is A? So we can work out what the energy is. Okay, so the energy, so this will rewrite in terms of I, not energy. We want to rewrite it in terms of E, and you can just go ahead and see that Q of T will become 2I by n omega sine theta, and P of T will also be proportional to root I, but some other dimensional grounds. You can fix the other factors. It becomes 2I n omega cosine theta. Okay, so exercise. What should this be equal to? For some bracket of Q and P. So what we are doing here, looking at the right hand side, okay, and so now I don't even write T's here because I shouldn't put T's here. Sorry, because it's just a change of variables. What should QP be?
Well,
1. Okay, because that implies that this is a canonical transformation. Is it clear? Okay. So we are done, and but of course here we can be explicit, but in my at least formally, okay, there exists action angle variables for any 1D potential. Okay. So for quartic case, I think it can be written in terms of elliptic functions. Okay. Excuse me, I have to throw someone out. Calibers. Okay. So, but the thing is, it will be less explicit than it has been there. But so this is one one fact to remember, that we can always find action angle variables for Hamiltonian systems with 1 degree of freedom. So let's go on to 2 degrees of freedom. Okay. So there are so-called methods of separation of variables, etc., which in some sense will you reduce things to one-dimensional problems, and then use the fact that every separated one-dimensional problems, and so you'll find for each one-dimensional problem you'll find one action angle variable. So you'll put them all together, and you will find that you can find action angle variables for all the degrees of freedom. Okay, but for 2 degrees of freedom, I'm going to choose a particular. Okay, so let me do this. I'll choose the degrees of freedom to be rho and phi. Okay. So phi is so this is like these are polar coordinates on R2 kind of thing. This is my coordinates, and phase space when the p rho and p phi are the conjugate moment. Okay. So I would write what the Hamiltonian is. The Hamiltonian is p rho square upon 2m plus p phi square upon 2m rho square, okay, plus v of rho. Okay, so what I'm doing here is that this is rotationally symmetric, okay, or a central potential. Okay, so question to you is, what does this mean? Is there something we get for free? Is there some action angle variable that we can get for free? So we want to get 2 actions and 2 angles. And phi is an angle. Okay. So let's do this. We'll choose I1 to be p phi, and we'll choose theta 1 to be phi. This is okay. So these are all constants. So now let's go back and work. So what I'm doing now again, it's a different method, but so I'll say H now is equal to P rho square by 2m plus I1 by 2m rho square minus plus V of rho. Okay, so this is what. So now what has happened is that this we will call V effective of rho. So we have an effective 1D problem, but what is the range of rho? Right, the domain, what are the values rho can take? Can it take negative values?
0 to infinity.
0 to
Infinity. Okay, thank you. Okay, so we have to remember this. And so then, so I2 which will be a function of E and implicitly and also E1, I1 which is already there. So let me just write something. I'll just define I2. I could probably define I2 now. So we have an effective 1D problem, and 1 by 2 pi integral of 2m E minus 2m V effective of rho. Okay, so we'll have some potential. Rho is only 1/2, so V of rho, V effective of rho is what we have got. And let's assume, so it blows up somewhere here, and then there is some structure. So I don't know, it could be something like this. Okay, so if we take and let it go up. Okay, let it go up. Okay, so something like this, because I want periodic potential. So if I get something like this, I get E. Okay, so then we'll have two turning points, O1 and O2. Okay, so again, now we can write I2 PDQ, so PD. Okay, so this is what we have to do, and there will be a theta 2 will be the variable conjugate to. Okay, so this is formally like what we did for the 1D problem. So in principle, we cannot do this integration. So for instance, even for so I don't know how what are the cases we can do the integration, but you can see that what we have is that theta 1, theta 2, I1, I2. Okay, and what will happen? What will happen is that what do I want to say? Uh, yeah. So these will be action angle variables. But I just want to say something, which is the following. If you look at the Hamiltonian, okay, Hamiltonian will now be a function of I1 and I2. And further, in general, what I want to say is that theta I will be some omega I, which will be a function of I1 and I2, T plus some constant. So, constant of integration. Okay, so what I want to point out here first, so remarks here are omega I generically will depend and omega 1 by omega 2 need not be commensurate, need not be rational. Okay, rational means there cannot be, a rational number, you know what it is, right? So it's something which can be expressed of the form of A by B, where A and B are co-prime and A and B are integers. Okay, in this case, positive integers. So they need not be rational. Okay, so first comment has to do with the fact that if you go back to the harmonic oscillator case, there we saw omega was a constant. Okay, it didn't depend on I. But even in the we know that even in the, if you go to a pendulum, once you go to large amplitudes, omega becomes, functions of amplitudes, etc. So then it will depend on I. Okay, so that's this statement. The second statement is more interesting. It says omega 1 by omega 2 need not be rational. Okay, so the point here is now what we have is a plane, which is the plane of, by plane I mean just I1 and I2 plane, and at any point there will be a torus, two circles. Okay, with angles theta 1 and theta 2. But now what this thing says is that the frequency, the first thing is that the frequency changes if you change your initial condition. Say this is point A and we take a second point on this plane, there's a different value of this thing, and so there will be a second torus. So motion will be so it will not move in B, but it will move on the surface of this torus. What I'm showing you here is that will depend. So the frequencies omega 1 and omega 2 will change from here to here. Is this point clear? That's the first point. Okay. Second point is also interesting, and this has to do with so let me draw things slightly different. This is also a torus, alternate representation. So this is 0 to 2 pi, 0 to 2 pi, and here this is theta 1 direction and this is theta 2 direction. Okay, but we know that 0 and 2 pi are identified with each other, so I identify these two together. And I mean, theta 1 is identified for theta 1 equal to 0 and theta. Similarly, theta 2 equal to 0 is to be identified with this. So maybe I can just count this. Okay, this is also a torus. Okay, so what happens? So first thing is what has. So let us look at motion. So how will motion be? It will be it will be so theta 1 will be some omega 1 t plus some constant, and theta 2 will be omega 2 t plus. Okay, so the thing is that if omega 1 is not equal to omega 2, so we'll have two different time periods, right? Omega 1 t1 equal to 2 pi, omega 2 t2 equal to 2 pi. That means that's when it will come back to each other. So what it says is that if omega 1 is not equal to omega 2, then t1 is not equal to t2. So let's say that for simplicity, t1 say. Then if you wait for time t1, theta 1 will come back to itself. But theta 2 hasn't come to itself because it is coming at some, because T2 is larger. Is this clear? It won't come back. So it's not periodic motion. Okay. Periodic motion means it should close. Okay. So what I'm saying is that if omega 1 by omega 2 is rational, orbit is periodic. Okay, simple case. I'll do case 1. When say, example, omega 1 by omega 2 is half. Okay. So that means, let's do it to be 2 by 1. Because I want T1. That's rational, right? So what this says is that this implies that T1 to T1 equal to T2. Is this clear? This is correct. Okay. So what it says is that, yeah, it is true if you wait till T1, theta 1 doesn't come, but if I wait for 2 time periods, it will come back. So this is periodic with period T2. Okay, so more generally, exercise. Exercise, show that if omega 1, omega 2 equal to A by B, and of course, we will assume that the GCD is 1, then period would be, then it is periodic. With what period you work it out. Yeah. With some period, determine this. Okay. Interesting cases, omega 1 by omega 2 is equal to irrational. What happens here? Can the orbits close? That means we want theta 1 to come back at the same time as theta 2. Anybody?
No, they won't close.
Yeah. But they can come arbitrarily close because you can always find a rational number which is a good approximation. Okay. So then what we have is we do not have periodic, really periodic orbits. Okay. Such orbits are called quasi-periodic. Okay, and cover and densely cover the torus. Okay, so if you wait long enough, you will get a picture of the torus. Do you understand what I'm saying? So if it is, classic example would be, suppose we have a periodic case, you will find the orbit will go like this. Let's say it goes around once and then comes back. That's it. Okay. What quasi-periodic thing will do is that after some time, the orbit will fill the whole thing. I can't even draw it. This is periodic. This is quasi-periodic. Okay. Actually, I would recommend that you try to plot these things, and you can plot it easily in this kind of square representation which I have shown here. Okay, you can plot the points on a computer. Okay. So one more thing is, on a computer you can only approximate irrational numbers by irrational numbers. So you will find orbits of fairly long period. That's about all you can find really on a computer. Okay. But if your accuracy is large enough, you may have to wait very, very long. So so you can approximate things very well. Okay, so I'll pause here. So I'll just finish with some remarks. Okay, first one is 2D isotropic oscillator. It's one example. So H here would be as we 2D. So I just have to tell you what the potential V of rho will be half m rho square. But we can actually do something more interesting. We can say that H is just, we can write in Cartesian. Actually, we can even do this, we need not x square or x1 square plus q1 maybe. Isotropy means omega, these two omegas are the same. So we can write this H as, p1 square by 2m plus half m omega square q1 square plus we can call this H1 and we can call this H2. Okay, so you can see that we can H1, from H1 we can go to some I1. That's for even if you write omega 1 omega 2 here, it will go to I1 omega 2, which like we did for the 1D oscillator, H2 will go to some I2 omega 2. Okay, it will be H prime 1 and this is H prime 2. Okay. So again, this is you get a different kind of action angle variables, which is the Cartesian version of that. Okay, so this is the first thing. Okay, second point is that so we are able to find. So for isotropic thing, there is p phi is also constant for isotropic. So we got three constants of motion. Okay, in four-dimensional phase space, what do you call such? If we can find 2n minus 1 constants of motion, what does it mean? So H1
super
H2.
integrable.
Yeah, so super integrable. Okay. So that's the thing. Also, the second thing is the idea of integrability. And we will environment. Okay, this is something which Arul introduced. Okay, so what does that say? Is that you should find n constants of motion in involution. You have to find f1, f2, fn of all these variables such that fi, fj pause on bracket is 0. This is involution. Okay. And you cannot find more than n for these things. And this is intimately related to the action angle variable story in the sense that these I1s, I2s they'll commute with each other. Okay. So, you say that these are integrable. So let's go back to, so claim is 2D isotropic oscillator is integrable. Integrable. So I have to give two constants of motion which commute. So can you tell me what the two would be? What your choice would be? H and P5. Angular momentum, LZ, which is P5. Okay, this is first. Same thing as 3D Kepler problem is integrable. Okay, so we have to, how many constants of motion have to give? 3. So what will be the 3? Last one, I need one more. You've forgotten, but it doesn't matter. It's L square. I can't put Lx. Why can't I put Lx? Lx is also a constant of motion.
Lx and Lg won't.
They don't
exactly.
commute.
They don't commute. Exactly. And we already saw this is super integrable. So these are examples. So I'm going to, in the last 5-6 minutes, why do we need the involution condition for integrability? And what I want to say here is these n constants of motion, with these can be the action variables suitably, or some functions of them. You can make them action variables. So if a system is integrable, you can always find action angle variables. Okay, that's the mantra. Okay, so why do we need the involution condition? And this is kind of very simple. If you look at, let's say we have theta 1 and theta 2, two angle variables. Okay, and so these would be some omega 1 t plus constant. This will be omega 2 t plus constant. The key point here is that these two guys, theta 1 and theta 2, they don't, you can move independently. They don't, there is no mixing of them. So what we need is, translations in theta are generated by I1. Okay. So this, omega t, which is translations, is generated by I1 and I2, and they have to commute with each other. These flows, so motion in the theta 1 direction and motion in the theta 2 should commute with each other. Okay, what do I mean by that? And so let's understand that. So let's say that F1 and F2 generate, we saw that they generate transformations in phase space, right, in our previous assignment. Okay, so what does that mean? It says that delta, so let's say X is, could be any, Q and P, any of those things. So delta of any xi, I goes from 1 to 2n, would be the Poisson bracket of x with f1. So we'll call this delta 1. Okay. Similarly, what will be delta 2 of x2? of the same itself. Okay. So what I have in mind is that so we'll put some epsilon here, epsilon 1 and epsilon. Okay. So what I have in mind is, suppose we are in this point in phase space and I carry out an infinitesimal f1 transformation, it will do some thing which is proportional to f1 times that cos omega. It will go here. If I did delta 2 first, it will go like this. It will come to the new point. Okay. Next, I can follow. First, I do epsilon 1, and then I do epsilon 2, the f2 generation. So I'll get something goes like this. Say epsilon 2. Okay. And this one, so I'm going like this, like this. Here I'm doing epsilon 2 first, and then I do epsilon 1. Okay. Now the point here is that these two may not be 0. So these 2 points may not be the same. Okay. If you want them, so we say a flow commutes, 2 flows commute if they, okay, so we say 2 flows commute if the points meet geometrically. Okay. Okay, so let us compute the mismatch. Okay. The mismatch is computed in the following way. I'm jumping some step, one step actually. Follows. So you just do delta 1, delta 2 minus delta 2, delta 1 acting on x. Okay, so let's first do delta 1, delta 2 acting on x1. So this is epsilon 2, okay, times commutator of xi with f2. Now I have to delta 1, but delta 1, epsilon 2 is just a number, so this will be epsilon 1, epsilon 2 times xi f2 f. Okay, so now we want to do the commutator. So now this is easy because I just have to exchange 1 and 2 on the right hand side here. Do that, you get epsilon 1, epsilon 2 times first term xi with f2 f1 plus, no, minus because it's a minus here. Is this clear? So all I've done is to take the difference of this computation, but then you can say that up to a sign, this is epsilon 1, epsilon 2. We can use Jacobi identity, and this is equal to, I'm putting this thing tilde here because I don't know if it is plus sign or minus sign, times xi with f2, f1. Okay. So the mismatch, so now what happens if they are in an involution?
Poisson bracket of
equal to 0. Okay. I'm using word commute. Okay. The flows commute actually. Okay. So this is the reason why in the Arnold Liouville-Arnold integrability criterion we require that these flows commute, and then okay, so only after this, okay, so this is important. So this is needed for motion to be on and n torus for integrable systems. Okay. So it's not some random thing. Okay. So the picture you should have in mind is this is some n-dimensional space of i's, and on top of it we have some n torus. This is achievable only for integrable system. So every point here would be some I1 to In, and the fiber is theta 1 to theta. Okay. I used the word fiber, sorry, I shouldn't. So that's what it's referred to. So I'll stop here. So the idea of action angle variables are quite interesting. And one more thing which I did not explain, why did we choose PDQ? Why not work with E? The PDQ is something called an adiabatic invariant, in the sense that if you vary parameters, okay, the functional form of I will vary slowly, will change, will not change to leading order. Let's put it that way. Okay, so if you change some parameter, omega might change, okay, because you change the parameter, but that's about it. Okay, so that's why it's chosen. This also plays a very important role in quantum mechanics in something called the Bohr-Sommerfeld quantization condition, where this action becomes n times h bar or something. Okay, so I'll stop here. Floor is open for questions.
Hello, sir.
Yeah. Yes, Bidhi.
So what does integrable systems refers in physical thing? Like, what is its physical meaning?
Physical meaning. That it means that there exist variables where this picture holds, where you fix the initial, so you've got n constants of motion, and you pick those are given by your initial conditions, and then motion will be restricted to some n torus. In general, generically it will be quasi-periodic, so it will fill the torus. So motion will lie on an n torus. Okay. So you can ask what happens in non-integrable systems. So you can take some integrable systems and try to deform it by adding some small perturbation, and then what you will see is that some of the quasi-periodic tori will disappear, some will remain. So this is there's something called the KM theorem, which you can look up, but it's a little bit more mathematical, so I'm not discussing it. But yeah, integrable systems are rare. Okay.
So,
Yeah.
when we don't have n constant of motion, like we have little less than n, like n minus 1.
Yes.
So will the motion be on n minus 1 torus?
Yes. So it would be like motion won't be just on n minus 1 torus, n minus 1 plus 2. There'll be some other p, right? Q and p, which you have not traded for I and this thing. So it will be, there'll be n minus 1 angles time and 2 other variables. Motion will be in that kind. It will be n minus 1 plus 2, so it will be in some n plus 1 dimensional space. Yeah. So this is partially integrable. So that is like that picture which Arul drew, right? If you have one constant of motion, you draw one thing a second, so it will go into some subspace. So, but you're right. If you find action angle variables, if you find m of them, then there will be an m torus, definitely. In involution. That's key.
And so, how I is defined like that? Is there like
no? I don't know. I don't know how to do it in general.
Okay.
There is some. I mean, you go case by case. That's what I said. Integral systems are rare. If you give them, we can write. We can do it. So you can look up probably Kepler problem. It will be given somewhere. Good question. Anything else?